Hi everyone. In the last lectures, a long channel device has been simulated. In this lecture, for short channel MOSFET, its input and output characteristics are calculated. First, we calculate the input characteristics. This figure compares ID versus VG curves for two devices. The drain voltage is small and the devices are in the triode mode. Since the drain current is inversely proportional to the channel length, the drain current is much higher for short channel MOSFET. For short channel device, the threshold voltage is reduced even at a low drain voltage. These figures show the input curves of two devices, long channel, short channel. I just made rough estimation on the threshold voltage by using the GMMax method. It is found that the threshold voltage is reduced by about 50 millivolt. It is stressed that the drain voltage is just 0.05 volt, so it is not related with the dibble. How do we have such a reduction? It is because of the charge sharing effect. The channel charge is not solely determined by the gate. The source and drain terminals also contribute the charge. This figure shows the conduction band profile at the interface. When the conduction band energy is determined by the gate terminal, this long channel value will be the peak conduction band energy. However, in the case of short channel devices, the channel is within a range affected by the source and drain terminals. So, the conduction band profile is deviated from that of the long channel device. As we can see here, the peak energy is reduced and it is related with the reduced threshold voltage. In addition to the charge sharing effect, which exists even at a low drain bias, the dibble also plays an important role at a higher drain voltage. For example, the dibble is measured at a constant drain current. Two intercepting points are measured, and from their difference, the dibble can be calculated. In this example, its value is estimated as 45 mV per volt. It is noted that this value is somewhat better than the actually fabricated device reported in the IDM 2003. Again, in order to understand the dibble in the short channel device, the conduction band profile is drawn at the interface. The gate voltage is 0 volt and two drain voltages are considered. At a high drain voltage 1.2 volt, the conduction band energy is decreased by 1.2 volt in the drain side. Therefore, even at the channel region, the conduction band is moved downward. The energy difference between the source terminal and the peak is now reduced. It means that the drain current is further increased with a high drain voltage. Now, let's move to the output characteristics. First, we simulate the device only with the inversion mobility model. In other words, the velocity saturation is not included. In this case, we can see that the output resistance of the MOSFET is not infinite. It is due to the channel length modulation. For long channel device, the length of a pinch-off region is negligible. However, for short channel one, it is no longer negligible. However, when the velocity saturation is further included, we have a significantly reduced current. The blue curves are result with the velocity saturation. It is clearly observed that the saturation occurs much earlier when the velocity saturation is included. Without velocity saturation, the saturation current is determined by the pinch-off. With the velocity saturation, before pinch-off becomes dominant, the electron velocity is saturated and it determines the saturation current. Therefore, the onset of saturation appears earlier. That's it for this lecture 13. In the next lecture, we will consider a P MOSFET. Thank you and see you later.